So now we're going to focus more on continuity in this video. By definition, a function is continuous at a point A if the limit of f of x as x goes to a is equal to the left-hand limit, and it's equal to the right-hand limit, and it's also equal to f of a. So if we want to check continuity at a certain point, we need to check if f of a is defined, and if it is defined, then what is that numerical value? The second thing we need to do is find the right-hand limit and the left-hand limit and see if they're equal to each other. And this will give us the overall limit, and we want to see if this is equal to f of a. If these three things are satisfied, then we know this function is continuous at that point, x equals to a. The first thing we're going to look at is a graph, and we're going to see where it's continuous. As kind of a general rule, you can find your continuity if you can draw a smooth curve without lifting your pencil. So if it's continuous, then you can draw the smooth curve. Without lifting your pencil. So just watch my cursor as I move through this function here. We're going to go from negative infinity, and then it seems to stop at x equals -1, including it because we have a closed circle. Then we continue on to the next piece of the graph. We have an open circle here. It's not included in our graph, so make sure you have a round bracket. And then it goes to 0. Again, we're not going to include 0 because there's an arrow to indicate it's just going on, and it's not ever going to touch 0, so you need a round bracket. And then from this part of the graph, we have 0 again, not including it, up until 1. Again, not including it. And then we can continue our graph from 1 to infinity. And that is the interval which the function is continuous. We are going to describe this function in terms of x. It's kind of like your domain in a sense too. So let's just say we're not given a graph and we're given the function, and it's a piecewise function. We want to find all discontinuities of f. So if you look at the two pieces, this is a linear graph, and this is also a linear graph. Both linear graphs, if they have no restrictions on them, they are continuous everywhere, and they go on forever. But because this is a piecewise function, it's possible that we might have a discontinuity at x equals -1. So that's what we need to check. But first, we're going to state that this is a polynomial, and they're continuous everywhere. So the function is continuous from negative infinity to -1 for this one, and then from -1 to infinity for this one. So we're going to state that first. The CNTS just means continuous. So we know f is continuous on negative infinity to -1 from this graph, and also from -1 to infinity for our 3x graph. Okay, so if I want to show that this function is continuous at x equals -1, I'm going to use the following three things. We're going to find f of a, or in this case f of -1. We're going to check the left-hand limit and the right-hand limit to see if they're the same. And if that's satisfied, then we'll check this last part here. So first things first, we're going to calculate f of -1. That would be your 2x plus 1. So I'm going to plug it into this part of my function. And that's negative 2 plus 1, which is negative 1. Okay, so there is an f of a. It's defined, but we don't know if it exists. We don't know if the limit exists. So we're going to check that next. So we want to check the left-hand limit. So that's 3x. Sorry, that's 2x plus 1. We're going to plug the negative 1 into that. It's negative 1. Now we're going to check the right-hand limit. And that's 3x. So that's 3 times negative 1, which is negative 3. These limits are not the same. That means number 2 is dissatisfied, and also our overall limit does not exist, and that's a problem there. So we're just going to say since the left-hand limit does not equal to the right-hand limit, f of x is discontinuous. At x equals to negative 1. And then that's it. Now if we want to list the interval in which is continuous, it's going to be everywhere except the point at x equals negative 1. And be careful, we need to take a look that we have to include negative 1 for 2x plus 1. So that's going to be over here. Make sure you have a closed bracket for that. So I would star this because you're going to use this for this entire section of continuity. Now we're going to go over some different types of discontinuity as well and classify them. The first one we're going to look at is jump discontinuity. We already saw an example of that, and I'm going to draw another one here. So it's usually when we have one part of the graph and it has a point that's included in the graph, and then this other part of the graph where it kind of jumps up in your y values and it's not included in the graph. So this is a jump discontinuity. At x equals a. Another type is a removable discontinuity. So holes and displaced points is what takes place in these type of graphs. So here's an example of a linear graph with a hole in it. A displaced point is a point that exists at x equals a, but it's not in the same y value. So here we have a hole at x equals a. You could also have an infinite discontinuity. This just means you have an asymptote, a vertical asymptote somewhere, and then the graph exists on either side of that asymptote. We can call this 0 along the y-axis. So we have an infinite discontinuity at x equals 0. So now let's do an actual example. Let's see if we can remove a discontinuity in this given function and then rewrite the function to remove it. Now we can tell that we're going to have a problem if x is equal to negative 3 because we're going to get 0 in the denominator. So we're going to state that first. At x equals negative 3, f of x will have a 0 in the denominator. It will tend to 18 over 0. So f of x has a whole or maybe a infinite discontinuity just a problem point in general, could be one or the other, when x is equal to -3. And this is supposed to have a negative here. Sorry about that. Because it would be an infinite discontinuity if it was x squared plus 9, but it would be a whole if it was x squared minus 9. And what I mean is x squared minus 9, because if it wasn't, then we can't remove the discontinuity because it's an infinite one. So if we want to remove this, let's look at the limit as we approach -3. You would want to factor the numerator. And then you can see you could cancel out top and bottom, x plus 3. Then we're left with x minus 3. If we were to substitute this -3 in to find the limit, that's -3 minus 3, which is -6. So that means our graph f of x given to us has a whole at x equals -3, y equals -6. So we have a whole there. We want to remove this whole. We can get rid of this whole if we redefine the function into a piecewise function. We'll just call g of x. So we'll include f of x where x can't be -3 because that was our whole area. And we're going to replace it with the point -6 at x equals -3. So once we include this point, it fills in the hole, and then now this is a function without a discontinuity.